I'm Nathan Gillett. I work for Environment and Climate Change Canada, and I'm going to be talking to you today about human influence on the 2021 Pacific Northwest floods. This is work that I did in collaboration with a number of colleagues who you can see listed on the screen now, both from Environment and Climate Change Canada and the Pacific Climate Impacts Consortium at the University of Victoria. So what I'm going to be talking to you today about is a strong atmospheric river event which occurred on the 14th and 15th of November 2021 and brought 2 days of intense precipitation, rainfall and some snowfall to southwestern British Columbia and northern Washington state. And this caused the costliest natural disaster in BC history. At least 5 people sadly were killed in landslides. And very significant infrastructure damage occurred. There was dike failures on the Tulameen and Sumas rivers in BC. The damage and closure of all the major highways, railways, and pipelines linking southwest BC to the rest of Canada. So Vancouver was essentially cut off from the rest of Canada for a number of days following this event. Insured losses in BC were estimated to be 675 million Canadian dollars by the Insurance Bureau of Canada, but the total costs from this event were estimated to be much higher than this. One estimate published by the Globe and Mail newspaper was around $9 billion Canadian. And the biggest contributor to that was rebuilding infrastructure, highways, railways, and so on following this event. Also in Washington state, the event had significant impacts. There was flooding on the Nooksack and Skagit rivers. A landslide closed I-5 following the event. So the impacts weren't restricted to BC. There were significant impacts from this event also in Washington state. And the questions that I'm going to be talking about in this talk are how large and how unusual was this event? And how has human-caused climate change increased the likelihood and the magnitude of this kind of event? And the analysis I'm talking about today was published in a paper in Weather and Climate Extremes. You can see the paper and the link to it there on the right. So you can look there if you have more questions or you're interested to find out more about the study. Okay, so I'll start by showing some pictures of the event. The photo at the top left is a bridge on the Coquihalla Highway on the Coldwater River. So any of you that live in this part of the world, if you drive from Vancouver into the interior of British Columbia, you probably are following this highway. And a number of bridges were destroyed on that highway following this event. The photo at the top right shows the Fraser Valley near Abbotsford. So that's inland from Vancouver. You can see the very extensive flooding, a lot of farms, a lot of agriculture severely impacted following the event. At the bottom left, that's near Lytton in the interior of BC. You can see there very significant damage to both, well, highways and railways there following the event. And then in the bottom right, you can see a satellite photo showing flooding of the Nooksack River. The brown on the photo is floodwaters. So you can see, as I said, there was very extensive flooding, not just in BC, but also in northwestern Washington state. Okay, so this event was caused by what we call an atmospheric river, and that's illustrated on these maps. The maps show the amount of water vapor in the atmosphere, and if you condense that water vapor out and you measure the depth of water, that's what's shown in this figure, the depth of the water in millimeters. So the dark green colors showing very moist air. And you can see that during this event, there was a filament of moist air stretching up towards the coast of BC, the coast of Washington state, from the subtropics, from the kind of Hawaii area, if you like. And this is what an atmospheric river is. It's this kind of filament of high moist air. And the arrows on the figure show the transport of water vapor. So where those arrows are bigger, that's where there's a lot of transport of water vapor. And you can see that in this event, there was a lot of transport of water vapor in this atmospheric river, impinging on the coast around that pink box there, which is our study area. One thing about this particular atmospheric river, it came more from the west, so more of a kind of east-west alignment than the typical events in this area, which come more from the southwest. And that alignment from the west, we think, aligned with the Fraser Valley and allowed water vapor to be transported further inland than is typical for other events in this region. If we compare the magnitude of this atmospheric river with other atmospheric rivers that in this area, averaging now over that pink box that I showed in the previous slide, in terms of the water vapor transported in the event, it was a strong event, but it wasn't that unusual. We estimate something like a 1 in 3 year event. If we focus just on the westerly events, so the atmospheric rivers that are coming more from the west, then it was about a 1 in 12 year event. So rarer when we focus just on those events that come from the westerly direction. Now, moving on to the next question, that's how atmospheric rivers have been affected or are being affected by climate change. We know that as the atmosphere warms, it can hold more water vapor. So we would expect that atmospheric rivers would be able to hold and transport more water vapor as the climate warms. And the analysis that I'm showing on this slide is based on simulations from a regional climate model called CAN-RCM4. And we ran simulations from 1850 and through into a future with increasing greenhouse gas emissions. And we looked at how atmospheric rivers change with the global mean surface temperature, or the global average temperature. And the figure that I'm showing here, on the y-axis, you can see the maximum water vapor transported in storms, and on the x-axis is the global mean surface air temperature increase. And you can see that there's a clear increase in the amount of water vapor, the amount of water that can be transported by these atmospheric rivers with global warming. Based on the estimated human-induced warming to date of about 1.1 degrees Celsius, we can infer that human-induced warming increased the probability of this kind of event by about, well, a best estimate of 76%. And the uncertainties on that is 64 to 93%. So based on this analysis, there's clear evidence that human-induced climate change increased the probability of atmospheric river events like the one that we saw in 2021. And with ongoing global warming, we can expect these events to intensify further. For example, at 3 degrees Celsius of global warming relative to 1850 to 1900, we estimate that the probability of these kind of events is projected to increase by a factor of 4. So a very substantial increase projected in the future. 3 degrees Celsius of warming is roughly the amount of warming that we could expect based on kind of current policies, but by the end of the century. Okay, so far I've talked about the atmospheric river itself, but now what about the rainfall or the precipitation associated with this event? This slide shows 2-day precipitation. So the event was really concentrated into a period of 48 hours or 2 days. And this slide shows the amount of precipitation, that's rain plus snow, that fell during the 2 days of this event. You can see that the rainfall during this 2-day period exceeded 300 millimeters, so exceeded about 12 inches in a number of locations, including in Vancouver Island, north of the Fraser Valley in BC, but also in Washington State in the kind of Mount Baker area of northern Washington State. And so 300 millimeters, 12 inches of rain in 48-hour period is a very high amount of rain. Also, we can, using the same data, we can look at how this event compares with other events in the past. In the graph at the bottom right, you can see the amount of precipitation in the wettest 2 days of each year. The brown line shows a Canadian data set called the Kappa data set. Based on that data set, we infer it was about a 1 in 100 year or 1 in 99 year event. Based on another data set, the blue line, the ERA 5 data set, we infer it was about a 1 in 47 year event. So based on the amount of rainfall that fell during this event, it was a pretty rare event. It was something like a 1 in 50 to a 1 in 100 year event. Again, we can look at the human-induced climate change contribution to this rainfall, and that's what is shown on this slide. We can look at basically averaging over that box that I showed you. We can look at the wettest 2 days of the year, and we can look at the distribution of that starting in 1850 to 1900, and that's what's shown in the green histogram here. And then we can compare that with the present day, or 2011 to 2030, which is what is shown with the brown histogram. And although those two distributions don't look very different, if we look at the heaviest events, or the events that are heavier than the 2021 event, which is shown with the kind of vertical brown line, we can see that the chance or the probability of this kind of event has increased by about 45% compared to 1850 to 1900. So there is a significant increase in the probability or the chance of events like the 2021 event due to human-induced climate change. And this analysis is based on output from a number of climate models from around the world. If we look into the future, under a scenario with global warming of 2.7 degrees Celsius, this increase is projected to be about 200%, so about 3 times as likely for events of this kind by the end of the century in a scenario with, well, 2.7 degrees global warming. So again, we can expect much bigger increases in the probability of this kind of event in the future. Okay, so I've looked at the atmospheric river event, I've looked at the precipitation associated with it, but the thing that impacts us most directly is stream flow, or the amount of water in rivers. And that's what I'll show in the last part of this talk. So what this slide is showing is showing the circles show the locations of stream flow gauges or hydrometric gauges in rivers around BC, and in fact 1 or 2 also in Washington state. And so we measured, or well, we're using data here that measures the peak stream flow during this event, and then we're comparing that with the peak stream flow in previous years. And from that, we can estimate from the distribution of the stream flow in previous years, we can estimate the return period for the 2021 event, like how often we would expect that kind of event to occur. And in on the map there, you can see that for a number of the stations, the return period varies for the stations across the study area. But for some of the stations, particularly in the east of the study area, the return period was more than 100 years. So we estimate that these kind of events, or this kind of an event, is a rare event, one that only occurs less than once in 100 years. You can also see, as I mentioned, this analysis extends down into Washington state. It includes the Nooksack Basin here in the south. The return period there is estimated at between 20 and 50 years. And some of these stations saw their previous records exceeded by a large amount. For example, for the Coldwater River, which I showed you a picture of on the top left, the Coldwater River exceeded its previous record by 82%. And then another river in the domain, the Tulameen River, exceeded its previous record over a 40-year period by 152%. So we saw more than twice as much water in that river, as we'd ever seen in the past 40 years. So a very extreme and unusual event in a number of these basins. Okay, and the last part of the analysis that I'll show you here is now an event attribution, or an attribution analysis for the stream flow. And for this, we used a hydrological model. So that's a model of the river basins around BC. This is focused on the Fraser Basin and its tributaries. And this hydrological model is driven by climate data from a climate model, and it simulates the amount of water, the amount of stream flow in the rivers. And using this model, we can look at how often we can compare the probability of high streamflow events in the current climate, and that's shown in the blue in those graphs to the right. So the graphs show the peak streamflow on the y-axis against the return period on the x-axis. And they compare in blue the current climate, 2011 to 2030, with the climate of the 50s and 60s, which is shown in the black and gray. And if you pick a particular return period, you can see that the peak streamflow for a particular rarity of event is substantially higher now than it was in the 50s and 60s. Or conversely, if you pick a particular peak streamflow and compare the return period for that in the current climate with the 50s and 60s, you can see that high streamflow events have become considerably more common due to the effects of human-induced climate change. And for all the basins shown, in fact, climate change has increased the risk of 100-year events, or a rare event, by a factor of between 2 and 4. So we're seeing very substantial increases in the probability of high streamflow events due to climate change. And the number one cause of that is the more intense rainfall that I've shown you already. But we do think that probably increased snowmelt associated with a warmer climate is also playing into this. Okay, so to conclude, in terms of the rarity of the November 14th and 15th event, in terms of the atmospheric river, we estimate it was about a 1 in 10-year event. But in terms of the 2-day precipitation, the rainfall associated with the event was substantially rarer, something like a 1 in 50 to a 1 in 100-year event, depending on the data set we use. And then in terms of stream flow, or the amount of water flowing in the rivers, it varied across the study area, but it exceeded a 1 in 100-year event in a number of locations in our study area. And across all 3 variables, we find that human-induced climate change substantially increased the risk or the probability of an event like the one that we saw in 2021. And these events, we've already seen the effects of climate change, but as the climate continues to warm, we can expect these effects of climate change to become more intense. So such events, including the atmospheric river, the extreme precipitation, and the flooding, will become more likely in the future with additional warming. Thanks very much.